Most people think computational fluid dynamics, CFD, is an advanced topic meant only for experts who understand complex equations. But the truth is that CFD was developed to answer a very practical engineering problem: how fluids will behave in real systems before we physically build them. Long before computers, engineers already tried to imagine flow patterns. CFD simply made those invisible patterns visible and measurable. To see this clearly, imagine a simple everyday situation where you blow air through a narrow straw and then through a wide pipe. You instantly feel that the airflow behaves differently, faster in the narrow section, smoother in the wider one. Without realizing it, you've already asked the same question. CFD answers: how does fluid speed, pressure, and direction change with geometry? What's actually happening here is simple. Fluids change speed, pressure, and direction when they move around objects or through spaces. And CFD predicts this behavior by dividing the fluid region into many small cells and solving flow equations inside each one. When all cells are combined, engineers can visualize velocity, pressure, turbulence, and heat transfer across the entire system. This same logic operates in real engineering applications. Aircraft aerodynamics are optimized using CFD. Car designs are tested for drag reduction. HVAC systems are analyzed for airflow comfort, and pipes and pumps are designed to avoid pressure losses and cavitation. Engineers use CFD to test hundreds of design variations digitally, something that would be impossible with physical experiments alone. The theoretical foundation behind CFD is built on fluid motion equations formalized by scientists like Claude-Louis Navier, whose work helped describe how viscous fluids move. Modern computers don't change the physics. They simply allow these principles to be applied at a scale and speed that humans never could manually. Now that you understand the intuition behind CFD and flow prediction, the next natural step is to explore laminar versus turbulent boundary layers and result interpretation, where we learn why CFD results can look impressive, but still be misleading if used incorrectly. And that's exactly what we'll break down in the next episode.